This is from Unit 6, Lesson 3, Part 1, Accumulation Functions, and it also includes the Fundamental Theorem of Calculus, Part 1. So we're going to start with where we've left off with the idea that we have a continuous function on a closed interval, and we're going to define some other function which represents the area under the curve between a and some point x. And you can see in this picture that x is in the interval between a and b. And we're going to denote this area under the curve as a definite integral, which we've been doing. And we're going to call this new function capital F of x. And as I said, x is between a and b. So here is where our new function is defined. F of x is equal to the integral from a to x of f of t dt. So for any value of x between a and b, this function, this new function, capital F of x, will give us the area between a and x. This is the definition of the first fundamental theorem of calculus. And it helps make the connection between integrals and derivatives, because you're going to see that if small f of x is a continuous function, capital of f of x is called its antiderivative. So every continuous function has an antiderivative. Okay, so here is the formal definition of that. So if f of x is continuous on the closed interval a to b, then g of x is equal to the integral from a to x of f of t dt. And f of that integral is continuous on ab and is differentiable on the open interval. And so we can say that the derivative of g is f of x. So there's where we get the antiderivative being g of x. An alternate notation can be seen using our df dx notation here, where we show that we're taking the derivative on both sides and we end up with small f of x. Okay, so how this works, we're going to work through a couple of examples here, and they're going to get more complex as we go. We have the graph of little f shown here. So g of x is going to be defined from negative 6 to x f of t dt. So we're to evaluate the following function. So g of negative 3. So what you want to notice, and this is going to become important as we go through these definitions, these examples, what is the lower bound of our function? How is g defined? So we need to find the area from negative 6, and now our x is 3. So this first equation can be defined as the integral from negative 6 to negative 3 of f of t dt. And so what we're going to do is we're going to have to find those areas. So a good way, you can divide this up however you want. I'm going to divide it up this way. So here is my first piece, and that's a trapezoid that has area 4. And then I'm going to do this little skinny trapezoid here that has area 2.75. I don't know why this is taking so long to respond. Apologize for that. And then I have this other trapezoid right here from negative 3 to 0, which is 5.25. And I'm going to keep going and just finish this off here. So then I divided it up in half here, and I got this piece from 0 to 4. Let me draw that a little straighter. To be 12 units, 12 square units. And then my last trapezoid here comes out to be 9 square units. So now I can do the entire problem. So the first one, g of negative 3, is going to take me from negative 6 to negative 3. So I need this area here. So what I'm going to do is I'm going to take 4 plus that 2.75. And when I do that, the value of this area is 6.75. Now the next one, g of 0, so I'm going to add in that other piece there here. So you can also do this by, there it is. You can also do this by showing it this way. It's going to be the integral from negative 6 to 0, or you can also do it as the integral. You can add the pieces. So you can take g of negative 3 plus the integral from negative 3 to 0 of f of t dt. And we're going to talk more about that as we go along. And so the value for b, I'm going to put it over here. G of 0, I'm going to have the 4 we already had plus the 2.75. And now I'm going to add to that the 5.25. So that's going to be a total of 12 square units. So that's B right there. Okay, G of 4, I'm not going to put the integral notation. Is now going to be everything we've had, plus we're going to add on our 12 here. So I'm going to put, it's going to be G of 0 plus the integral from 0 to 4 of f of t dt. So that's going to be my 12 plus another 12 for the piece we did in this section. So C is 24. And then finally the last piece is going to be just adding on that 9 there. So this is going to be my G of 4 plus my integral from 4 to 7 f of t dt. So that's going to give me 24 plus 9, which is 33. So you can do your integrals, your definite integrals, by chunking it up in those pieces like that. Okay, so next example. So what we have here is f is the graph of the function shown at right, where capital G of x is the integral from 0 to x of f of t dt. So we are to complete this table. Let me pull this, see if I can pull this table, make it, I think that's the whole table. All right, and so we want at 0, 0 to 0. So we're going nowhere, so that means that we have no area because there's no width whatsoever to that section of the graph. It's from here, here to here. So it's nothing. Okay, next piece. G of 1. So we need this section right here, this rectangle right there, which is a 1 by 2 rectangle, so it is going to be 2. The next piece. The input is 2. We don't have everything filled out this time, so we're going to put our 2 here, and that means our integral is going to be 2. So we can add on this trapezoid to what we already did, and we're going to have another piece, which is that trapezoid is 3 units. This is 2. So adding those together, we get a total of 5 square units. And then we want G of 3, so we're going from 0 to 3. And so then we have to add on the area of this triangle, which comes out, it's 4 units high and 1 unit wide, so that is 2 units. So adding those together, we get 7. And then G of 6 is going to go from 0 to 6. And so then we have all of this area here. So let me just finish filling out the parts. So let's do this triangle. And that triangle is 2 wide by 2 high. So that's going to be 2. And then I have another rectangle that's 2. And then I have another triangle, which is 2 high by 1. So that's going to be 1. And let me just make a little note here that because we're below the x-axis, these areas are going to be, when we add them up, they're going to be negative. So our value at 6 is going to be the 7 we already had here till 3, and then if we go to 6, which is here, we're going to have to subtract off those 2 pieces. So we have 7 minus 4, which is 3. And that does not look like a 3. And then finally, f of 7 is we're going to take up to 6, and then we're going to have to subtract off that last piece. So 3 minus 1 is 2. Because it's on the other side of the x-axis. And remember, we define our area to be positive above the x-axis. So letter B then asks us, and I think I'm just going to reduce this in size so we can see the graph still. Letter B asks us on what intervals is g of x increasing. And g of x is going to be increasing from 0 to 3. And my reasoning is, remember, this graph is really g prime of x, its derivative. So it is going to be increasing where g prime of x is greater than 0. So that means where f of x is greater than 0. So that's between 0 and 3. Okay, next question. I don't want to make this too much smaller, so I'm going to have to scroll. Where does g have a maximum? So that's where it's going to change signs from increasing to decreasing. So that's going to happen at 3, 3,7. That's the maximum value because f changes signs from positive to negative because g will be increasing where f is positive, and then it will be decreasing where f is negative. So this graph has changed from positive to negative here at 3. So g is going to be a maximum because it was increasing, it's changing directions, and it's decreasing now. And we can say that because, remember, our f is a continuous function. Okay, next question. Sketch the graph. Okay, so let's put both these on here so we can see them. And we're just going to lay this out. Now we know that we have a maximum at 3,7 because we get the 7 here from our table. I didn't mention that when we were writing down where the maximum was. We know 0 is going to be 0, and we're just plotting the points in our table. So we have 1, 2. I should have a point there. There we go. 1, 2, and 2, 5. And then we have 3, 7, which we plotted. Then we have 6, 3. And then we have 7, 2. And then we can connect these because we're dealing with continuous functions. Like, whoops, I shouldn't go past 7. I was afraid of that. Okay. There we go. Like that. Okay. Next question. Example 3 says, let's make this a little bigger now. Let's examine what would happen geometrically to capital F of x defined from 0 to x f of t dt if we allow k to take on different values. So in other words, what happens if we change the lower limit of our integration? So we're going to deal with that in different ways, and you'll see as we go along how this works out. So at 0, we're going to have no area here. So f of 0 is going to be 0. And at 1, we have this little tiny triangle here, right there. And it's half of a 1 by 1 block, so that's 1/2. And then at 2, here we go, we have this bigger triangle, if you want to do it that way. And so that is going to have a value of 2 because it's the base is 2, the height is 2, and you take half of that, so you get 2. And at 3 then, now we can add on to that this trapezoid right here. And when we do that, that's going to be another 2.5, that trapezoid, so we get 4.5. I'm not writing the numbers in there because it's so tight. And then add 4, now we're clear to here. So if you just want to find that area of that triangle, you can do that. It's 4 over and 4 high. So it's going to be half of 16, which is 8. Okay, now for part B, it asks us what is the domain of f. It's going to be whatever is defined for f of t, and we can see from the graph that our domain is defined from 0 to 10. And our next question is, use the concept of area accumulation to complete the graph of f. Plot the points in your table in blue. So what I'm going to do before I plot my points is I'm going to add some points because I only have from the table up to 4. So I'm going to continue this table here, and I'm going to do the rest of the areas from 5, 6, 7, 8, 9, and 10. Okay, so then at 5 then I have another trapezoid to add on to my 8, and when I do that, that trapezoid ends up having an area of 3, so my area here is going to be 11. And then at 6 I have that little triangle that ends up, it's 2 up and 1 over, that's 1 more, so that's 12. And now notice now at 7 we are now below the x-axis, so that's a little off, but I'm just going to, just for simplicity's sake, I'm going to say that that is another little half triangle, so I'm going to subtract a half and get 11 and a half. And then at 8 I am going to subtract off that little trapezoid, and so that has an area that leaves me with 9 at 8, and then at 9 I have another trapezoid right there, and that area then leaves me at 7.25, and then finally at 10 I'm subtracting off another half there, and I get 6.75. Okay, and I know a couple of those are a little off, but I rounded them. You're more than welcome to be more accurate if you want, but it's just the idea of being able to draw this. Okay, so let me draw it in another color. I've been using blue, so let me use green. So I'm just going to plot all these points. Okay, so there's the graph. I just went ahead and plotted those real quick, and that's what our g of x looks like. And now we're going to answer some questions about, I'm sorry, it's not g of x, it's capital F of x. So where is the 0 of f of x? I'm going to make this a little smaller so we can kind of look at the graph and answer the questions at the same time. So where is the 0? It is at x equals 0. As you can see. What is the total change in f? So the total change is going to be the value at 10 minus the value at 0. And since it's 0 over 0, it's the value at 10, so it's 6.75. How does the total change in f compare to the net area bounded by the graph? And what you notice is it's exactly the same, because that's where we got the value of f. What is the maximum value of f? Well, that was the 12 we found. Where does this occur? And that's at x equals 6. And what is the range? And we can see the range goes from our 0 value to 12. And you can see we can still answer questions about our function, even though now we're starting with our derivative and we're using it in a different way and finding the antiderivative. So this is the end of part 1 of the video. We are going to pick up with some more examples in part 2.